All right, second last functional group, carboxylic acids. So once again, these are a hydrocarbon derivative. They're a derivative because they have oxygen in them, okay? So a carboxylic acid is anything that contains what we call our carboxyl group. So a carboxyl group is this COOH. Okay, so anytime you see a molecule that formula ends with COOH, it means it's carboxylic acid, right? So vinegar or acetic acid, which you've been using for years, which is CH3COOH, it's a carboxylic acid because it has that carboxyl group. So when you see it in a diagram, generally you're going to see it like this, right? Where here's that C, and then here's our double bonded O, and then here's a single bond to an OH. Okay, what's going to be different is what's over here. It could either be a hydrogen, it could be 1 carbon, 2 carbons, 3, I'm saying carbons? Yeah, carbons. Hold on, my kids are yelling. Give me a second. Okay, so anytime you see the C double bond O bond OH, you have what we call a carboxylic acid. So as the name suggests, these are all weak acids, okay? So the other thing that's a little bit different about carboxylic acids is their names are finally going to have a space, right? Every other name that we've done so far, there have been no spaces, right? It's just been numbers, letters, dashes, commas. Once we get into carboxylic acids, we are going to have a space in the name, and that's because there's going to be our name, and there's going to be a space, and then there's going to be the word acids. So when you're going the other way from a name to a formula, not a name to a formula, from a name to a diagram, it's usually pretty easy to know you have a carboxylic acid because it ends with acid and nothing else does that, okay? So when you're naming them, step 1, find the root, right? That's always our first step, find the longest chain. Your carboxylic acid must be part of that chain. And specifically, you're going to find that that C, that's part of that C double bond O bond OH, has to be carbon number 1. And that's because a carboxylic acid is like the highest priority. So it's always going to be assigned number 1. So the one nice thing with carboxylic acids is there's no decision making about what gets to be number 1. It has to be that carbon, okay? So your suffix, it says drop the E at the end of the name of the parent alkane and replace it with oic acid. So what you're generally going to find is that these are all going to end with an, oic, and then a space, and then the word acid. Okay, so we could have ethanoic acid. That would mean 2 carbons, where the first one has a double bond to O bond OH. We could have propanoic acid, butanoic acid, all kinds of things, okay? Prefix, any side chains that are there. We don't have to worry about how to assign numbers because there's only one way to assign numbers. So when we go to put that prefix together, it's going to go in alphabetical order. Do make sure that you are including numbers though, because we do need to indicate where those things are going to be located. Okay, so some examples for you. Okay, so here's our first one over here. Right, so again, it's kind of that hybrid diagram where we have a little bit of a line diagram, but then we also have some condensed structural. So important to remember that we have a carbon hanging out here and another carbon hanging out over here, right? And there's obviously some H's on this guy, but they're not shown because it's partly a line diagram. So I'm going to recognize that this is a carboxylic acid because I have that double bond O bond OH. Okay, you'll notice here how that OH is written, right? It's written HO, just like we talked about with alcohols. When we are writing it kind of on this side of our picture, the H is going to come before the O because the O has to also have that bond to it, right? That bond can't go to the H, it has to go to the O. So we want to make sure that that's shown here, okay? So prefix-wise, this has no prefix. And it has no prefix because there's nothing attached here and there's no random things attached here, right? We just have a regular alkane chain here. So when we go to name this, we have 1, 2, 3 carbons, hence the prop, right? Prop is for 3. Then because this is a carboxylic acid, and I know it's a carboxylic acid because the double bond O bond OH, it's an, oic, then space acid. So propanoic acid. Okay, now we move over to this one over here. Don't worry, no one's killing my children. They're just playing a game. I think hackers. I don't know what it is. So here we have this other molecule. So again, here's the carboxylic group. So we have the carboxyl. So we have a carbon here. Oh, I skipped this one. Here. Here. And then obviously this one here and these two here that are shown to us, okay? So this has to be carbon number 1 because of the carboxyl group. So longest possible chain would be to go 1, 2, 3, and 4. Okay, so in this case, we are going to have a prefix, and we're going to have a prefix because we have this methyl group and this methyl group over here. So 2 methyl groups, it's going to be a dimethyl. They're both off number 2. So even though they're both off number 2, we still have to put both 2s. So 2, 2 dash dimethyl. Okay, there's no other side chains. We have 4 carbons at our main chain, so bute. And then because this is a carboxylic acid, and we know that because we have the carboxyl group over here, anoic acid. So 2,2-dimethyl butanoic acid. So physical properties. We are going to go back to talking about physical properties for our carboxylic acids. So similar to alcohols, they have those oxygens. In fact, they have 2. So this actually means that carboxylic acid is highly polar. If I was comparing a carboxylic acid to an alcohol, for the most part, the carboxylic acid is more polar because it has more O's, okay? So carboxylic acids have LDFs because all moleculars have LDF. They have a dipole-dipole because they're polar, and they have a hydrogen bond because they have that OH, okay? So boiling point, what we're going to find is a very similar pattern as we did with alcohols. We're going to have that check mark pattern happening again. The difference, though, is where that check mark pattern is located. Okay, so this is kind of the pattern we've had so far, right? When we've been comparing melting points and boiling points to number of carbons, right? The red line here is our alkanes. Our blue line is alkenes because they had fewer electrons, so weaker LDFs. Our green line is our alkynes. Even though they had less electrons, they had a straighter shape, which is why we said they had stronger LDFs when we put them up here. And then purple up here is our alcohols, right? We had that check mark pattern because we said they had LDF, dipole-dipole, and hydrogen bonds when they were small, but that the dipole-dipole and hydrogen bonds got weaker as it got bigger, which is why it came down, and then it basically came down just to LDFs, which is why it went up. So now what we want to do is we want to add in our carboxylic acids. So they're going to follow the same pattern as our alcohols did. They're going to have that check mark. You're going to have it for the same reason. And that is because the small ones are polar. They have dipole-dipole and hydrogen bonds. The bigger they get, the weaker that force becomes. And then eventually those forces go away and it comes down just to London dispersion force. So same shape as alcohols, but they're going to be above an alcohol. Okay, why they're above an alcohol? Well, they have 2 O's. Most alcohols only have 1. So because of that, they get ranked higher. Okay, so we're now going to have our carboxylic acids up here as that gray line, right? So you definitely can just be adding to your original graph. You don't have to be making a new graph every single time, right? You can kind of have one little graph that you kind of keep track of all of these different melting point and boiling point patterns on. Okay, solubility wise, they're polar. Things that are polar are soluble in water. So they are, for the most part, going to be soluble in water. Obviously, same deal as alcohols. The bigger they get, the less soluble in water they will become, and they will most likely become soluble inside of hexane. The exception to that would be this molecule, benzoic acid. So that benz should be kind of saying to you, wait a second, do we have benzene? And we do. So here's our lovely benzene. Right, so we have a hexagon. I didn't quite connect that, but you guys can connect yours. I'm just going to throw that circle-ish shape in the middle. So there's our benzene. So if we want to make it anoic acid, that means it has to have that double bond O, bond OH. Now normally we'd be like, okay, well, we're just going to pick one of these 6 carbons and we're going to tack that on, right? So we're going to be like, oh, let's throw that here. Now don't actually do this. And I'll show you why you're not going to do this in a second, right? So if we did this, what would the problem be? Well, there's a pretty obvious problem. That obvious problem is this carbon hanging out right here. It now has 1, 2, 3, because remember there's that triple bond, 4, 5, 6 bonds going to it. You can't have 6 bonds going to a carbon. The max number of bonds is 4. So how we address that? We put in a C to any of these 6 carbons, doesn't matter where. And that C is going to have that OH and that double bonded O as well. Okay, so you could have technically put this COOH on any of these points and they would all be benzoic acid. Okay, so something like benzoic acid would probably be soluble in benzene because it has that large benzene structure, which is going to outweigh the polarity from this little bit over here. Okay,